Hey everyone, and welcome to another deep dive. This time we're taking on The Road to Reality by Roger Penrose.
Ooh, yeah, I've heard of that one.
Yeah, it's pretty mind-bending stuff, but
Mm-hmm.
super fascinating. We're going to try to break down some of the key ideas and see how they connect to the way our universe actually works.
Yeah.
So,
So
what's the big picture here? Well, Penrose kicks things off with this idea that the precision of natural laws, like the laws of physics, is what leads to the order we see all around us.
Yeah. I mean, think about it. Everything from
Like,
like how planets move to the way.
why does a seed always grow into a tree
Yeah.
and not just turn into like a rubber chicken or something?
Exactly. It's because there's this underlying precision to the way nature operates. Penrose uses this character in the book named Amphos to kind of represent this idea.
Okay.
Amphos believes that without this precision, the world would just be pure chaos.
Yeah.
It's like there's this built-in blueprint that makes sure everything works in a specific way.
A blueprint. Huh. So what is this blueprint according to Penrose?
Well, he argues that it's mathematics.
Math.
Yeah. He even goes so far as to say that these perfect mathematical forms exist in their own separate reality.
Well, hold on. Their own reality.
Yeah, he calls it the Platonic world of mathematical forms.
Okay, so it's like there's this...
It's like the concept of a perfect circle.
Yeah.
You know, we can try to draw one, but it'll never be truly perfect.
Right.
But that perfect circle exists as an idea, as a concept.
I'm following you.
And Penrose suggests that these ideal mathematical forms are what gives structure and stability.
Okay, so math is the universe's blueprint. But then there's this whole idea of the unreasonable effectiveness of mathematics.
Oh, yeah, right.
Like, why is math so incredibly accurate at describing the universe? It's kind of freaky.
It really is. Penrose dives into some examples that really show this off.
Yeah, like what?
Well, for example, the predictions made by quantum electrodynamics
Oh, boy.
are accurate to something like 1 part in 10 billion.
1 part in 10 billion.
I know it's hard to even imagine that level of precision.
That's like predicting the exact number of grains of sand on all the beaches in the world.
Yeah.
And getting it right. Okay, so math is powerful, but then Penrose throws us a curveball with this thing called hyperbolic geometry.
Oh, yeah.
It's geometry, but all the rules we learned in school go out the window. Parallel lines can meet, and angles in a triangle don't add up to 180 degrees.
I mean, it does sound a bit like something out of Alice in Wonderland, doesn't it?
Totally.
Oh!
But why bring up this weird geometry?
Well, because it challenges our assumptions about what geometry even is.
Okay, so
It forces us to rethink.
we're stepping outside of our normal reality to
Never.
see things from a new perspective.
Exactly. It's like we live on the surface of a sphere, the Earth.
Yeah.
To us, it feels flat locally, but that's only because we're experiencing a tiny part of a much larger curve.
Ah, I see.
Hyperbolic geometry is like exploring a different kind of curved space, where the rules are different, but the underlying principles are just as valid.
And didn't M.C. Escher, that artist with all the trippy artwork, use this in some of his pieces?
Yeah, he did. His woodcut circle limit eye is a great example. He used a technique called conformal representation.
Conformal representation. Okay.
Yeah. And in this representation, straight lines in hyperbolic geometry are shown as circles within a boundary circle.
So all those crazy repeating patterns and distorted shapes in Escher's work, they're not just random. They're based on this mathematical framework.
Right.
Pretty cool.
Yeah.
But how does this connect back to the real world or to understanding the universe?
Well, this is where things get really interesting. Hyperbolic geometry, as abstract as it seems, is actually relevant.
Oh, really?
Yeah, to understanding the curvature of space-time as described by Einstein's general relativity.
Wow. So by venturing into this bizarre world of hyperbolic geometry, we can actually gain a deeper understanding of it.
Exactly. It helps us to understand how
The fabric of reality.
even concepts like space-time curvature can be seen in a clearer way.
I'm starting to see how this all connects. Okay,
Yeah.
so we're using these alternative geometries as tools to expand our understanding of the universe. But let's shift gears a bit.
Okay.
Penrose also talks about how even basic concepts like irrational numbers were once a huge challenge.
Oh, yeah, for sure.
Remember the Pythagorean theorem? A squared plus b squared equals c squared?
Yeah.
Seems simple enough, but then you try to calculate the diagonal of a square,
Yeah.
and suddenly you're dealing with the square root of 2,
Oh.
which is an irrational number, and it throws everything for a loop.
It really did. The discovery of irrational numbers like the square root of 2 was a major turning point in math.
Yeah, because...
It forced mathematicians, especially the Pythagoreans who thought all numbers could be fractions, to totally rethink their understanding of numbers.
So it was a crisis, but also a breakthrough.
Definitely. It pushed them to grapple with infinity.
Infinity.
Which was a huge conceptual leap.
Yeah, I can imagine.
They had to move beyond just finite calculations and embrace the idea of processes that go on forever.
Okay, so did the ancient Greeks ever manage to fully define real numbers?
Well, they make some good progress. Eudoxos, who was a student of Plato, actually came up with some crucial ideas that laid the groundwork for it, way back in the 4th century BC.
Wow, that's a long time ago.
Yeah, it is. But a truly satisfactory definition wouldn't come around until the 19th century.
The 19th century, wow. So it took centuries.
It was a long and fascinating journey to really nail down.
To define something as basic as a real number, speaking of numbers that challenge conventional thinking.
Oh, yeah.
We can't forget about complex numbers.
Right.
I'll admit, I always found those a bit intimidating. The idea of taking the square root of a negative number just seemed impossible.
Well, they do sound a bit like mathematical magic, don't they? This mysterious I, where I squared equals -1.
Yeah, it's mind-bending.
But believe it or not, complex numbers aren't just some theoretical curiosity. They're actually super important in various branches of physics, from electromagnetism to quantum mechanics.
Okay, I'm ready to dive into the world of complex numbers. But can we start with something a little less intimidating than the square root of -1?
Sure. The key is to think about them visually. Imagine a number line, but instead of just left and right, it also extends up and down. This creates a 2D plane called the complex plane.
So it's like a regular number line, but with an extra dimension.
Exactly. And each point on this plane represents a complex number. And now the magic of multiplying by I is that it rotates any point on this plane by 90 degrees.
Wait, so multiplying by I is like spinning it on this plane.
It is.
That's a cool way to think about it.
And it makes that weird equation I exponential 1 much easier to understand.
How so?
Well, if you rotate a point by 90 degrees twice, you've essentially rotated it 180 degrees, which is the same as flipping it to the opposite side of the number line.
Right.
And that's basically what taking the negative of a number does.
I'm starting to get it. So by visualizing these complex numbers geometrically, we can actually demystify this imaginary concept.
Exactly. And this is just the beginning of our journey with complex numbers.
This is just the beginning. Yeah. Stick around because we're about to head even deeper into the road to reality. All right, we're back and ready to dive even deeper into Roger Penrose's The Road to Reality. Just to recap, we kick things off by exploring Penrose's argument that the precision of natural laws, like the laws of physics, is what brings order to the universe.
Right. We talked about how without that precision, the world would just be chaos.
Yeah, it'd be a pretty wild place.
Total chaos.
And we touched on this idea of a Platonic world of mathematical forms.
Yeah, that's a really interesting one.
Suggesting that these perfect mathematical shapes and concepts exist.
Independently of the physical world.
Right. Like a perfect circle exists as an idea, even if we can never perfectly draw it.
Exactly.
Then things got a bit mind-bending with hyperbolic geometry.
Where parallel lines can actually meet.
Yeah, and triangles don't add up to 180 degrees.
Right. But we learned that exploring these alternative geometries can help us understand things like space-time curvature and Einstein's general relativity.
So it's not just some theoretical curiosity. It actually has real-world applications.
Right.
And of course, we can't forget our journey into the world of irrational numbers.
Like the square root of 2.
Which threw the ancient Greeks for a loop.
Oh, yeah. It challenged their whole understanding of numbers.
It's amazing how a concept that seems so simple now was once a major puzzle for mathematicians. And we ended part 1 by dipping our toes into the fascinating and sometimes intimidating world of complex numbers.
Yeah, those can be tricky.
But we talked about how visualizing them geometrically can help us make sense of them.
Yeah, the complex plane is a really helpful tool for that.
Exactly. So we're thinking of complex numbers not just as abstract symbols, but as points on a plane.
And that makes the idea of multiplying by I as a rotation much more intuitive.
So instead of just memorizing formulas, we can actually picture what's happening. Okay, so now that we've recapped all that, what's next on our adventure through the road to reality?
Well, Penrose takes us even deeper into the world of complex numbers with something called holomorphic functions.
Holomorphic functions? All right, I'm all ears.
Now, these are complex functions that have a special property. They're surprisingly rigid in how they behave.
Rigid? What do you mean by that?
It means that if you know how a holomorphic function behaves in a small region, you can actually determine how it behaves everywhere.
Wow. So it's like a puzzle piece, where if you know the shape of one edge, you can figure out the whole piece.
That's a great analogy. And this rigidity is related to a concept called analytic continuation.
Analytic continuation. Okay, I'm following along.
It's a way of extending the domain of a function beyond its original definition.
So we're basically taking a function and making it work in more places than it did before.
Exactly. And Penrose uses the example of the logarithm function to illustrate this.
A logarithm. Yeah, I remember that from math class.
So the logarithm function normally isn't defined at 0.
Right, because you can't divide by 0.
But using analytic continuation, you can actually extend its definition to include other points in the complex plane.
So it's like we're filling in the gaps in the function's domain.
Exactly. And this process of extending the function's domain is what we call analytic continuation.
So it's kind of like we're giving the function superpowers, making it work in more places than it could before.
And what's really mind-blowing is that this concept of analytic continuation has major consequences in physics.
Really?
How so?
Well, it's particularly important in quantum theory and string theory.
Wow. So we're talking about extending the reach of a mathematical function. And somehow that has implications for the quantum world and even the fabric of space-time.
It's pretty amazing how these abstract mathematical tools become essential for tackling some of the biggest mysteries in physics.
Right, so holomorphic functions and analytic continuation, they're not just mathematical curiosities. They're actually helping us understand the universe at a fundamental level.
And Penrose doesn't stop there. He takes things a step further with twistor theory. Twistor theory. Okay, now we're getting into some seriously advanced stuff.
It is a complex theory, but the core idea is pretty elegant.
Lay on me.
Twistor theory aims to provide a different way of describing space-time using complex numbers and something called twistors.
Twistors? What are those?
Well, imagine you want to describe a particle. You usually talk about its position and its momentum separately.
Okay, like where it is and how fast it's moving.
Right. But a twistor combines both of those aspects into a single mathematical object.
So it's like a package deal for describing a particle.
Exactly. Location and movement all rolled into one.
And what's so special about these twistors?
Well, twistor theory suggests that space-time itself can be thought of in terms of these twistors.
So instead of points in space and time, we're thinking about these twistor objects.
Right, and by using twistors, Penrose argues that we can gain a deeper understanding of some of the most challenging problems in physics.
Like what?
Like the quest to unify general relativity and quantum mechanics. The whole problem of quantum gravity.
Yes, the holy grail of modern physics.
Oh, yeah. Exactly. And twistor theory offers a new perspective on this challenge.
So Penrose is always pushing us to see things from new angles, encouraging us to look at the universe through these different mathematical lenses.
He definitely is. And that's what makes his work so thought-provoking.
It's both exhilarating and humbling to realize how much we still don't know about the universe. But I guess that's the beauty of science. It's an ongoing journey of exploration and discovery.
Absolutely. And The Road to Reality is a fantastic guide for anyone who wants to embark on that journey.
We've covered a lot of ground already, from the precision of natural laws to the mind-bending world of twistor theory. But there's still more to come. In Part 3, we'll delve into some of the key takeaways from Penrose's book, and we'll leave you with some thought-provoking questions to ponder. So stick around for the grand finale of our deep dive. Okay, so we're back for the final leg of our journey through Roger Penrose's The Road to Reality.
Yeah, I feel like we've been through a mental marathon here.
It has been intense, but so worth it.
Oh.
Just to recap, we started by talking about how the precision of natural laws is what leads to order in the universe.
Right. It's like there's this built-in blueprint that ensures everything works in a very specific way.
And that blueprint, according to Penrose, is mathematics.
Yeah, he really emphasizes that math isn't just a tool for describing the universe. It's actually woven into its very fabric.
Right. Like the universe is inherently mathematical.
Yeah.
And by understanding its mathematical underpinnings, we can unlock some of its deepest secrets.
Exactly. And we saw that even the most abstract mathematical concepts can have a huge impact on our understanding of the physical world.
Yeah, like a hyperbolic geometry, which helps us understand the curvature of space-time.
And complex numbers, which are essential for various branches of physics.
It's amazing how these seemingly obscure mathematical ideas can actually help us grasp the workings of the universe at a fundamental level.
It's like we're peering behind the curtain and seeing the code that makes reality run.
But I think what really struck me about Penrose's book is how he doesn't shy away from those big philosophical questions.
Oh, yeah. For sure. He's not afraid to tackle things like the role of consciousness in quantum mechanics, or even the nature of reality itself.
Right. He's always pushing us to question our assumptions and to embrace the mystery that still surrounds so much of what we know about the universe.
I think that's one of the most important takeaways from The Road to Reality, the realization that our scientific journey is far from over.
There's still so much we don't know, and countless mysteries yet to be unraveled.
Absolutely. Penrose leaves us with a sense of wonder, a thirst for knowledge, and a deep appreciation for the interconnectedness of math physics and the human desire to understand the universe.
Well said. So if mathematics is indeed the language of the universe, what other secrets might it hold waiting to be discovered?
And could exploring those abstract mathematical realms actually lead to breakthroughs in our understanding of the physical world?
Maybe even challenge our very assumptions about the nature of reality itself.
Those are some pretty big questions to ponder.
They are, and I think that's a perfect note to end on. So to all our listeners out there, we highly recommend checking out Roger Penrose's The Road to Reality if you want to embark on this fascinating journey of exploration. Until next time, keep diving deep, keep seeking knowledge, and keep questioning the very fabric of reality.